we're gonna do a lot of that in this class, okay? So for those of you who just logged in, I was asking about how do you feel about Excel? Do you feel that you know enough to do all the data processing of this class? Because we're gonna do it a lot. And the best way to get into it, the best way to feel more confident about it is just to practice. Okay. If you want to practice one-on-one with me, just we can set a meeting for that. Okay. But you gotta tell me. You gotta request it. Otherwise, I just want to assume that you are all set with it and you're gonna be able to do all the processing. Okay. So being 10:32, I would like to start. So I'm just gonna switch to my tablet.
Okay. I got a quick question for you.
Yeah.
So how do you find out, I must have missed it if you had said it, how do you find out what lab section you're in?
So are you doing the in-person lab or the remote session?
I must have missed something because I never really saw an option.
So at the beginning of the semester, I was communicating. Sorry, at the beginning of like 1 week prior the first class, I was communicating with the students. Would you like to come to campus and have the in-person session, or would you like to do the remote version of the lab? Which one would you choose?
I see. I was added to the course later, so I must have missed that.
I see. So that's fine. Just shoot me an email once we're done with the class, letting me know your preference, and I will set everything up for you to. If you decide to do the in-person class, I will set everything up.
Okay, sounds good. Okay. Thanks.
Yep. So I'm just going to. I'm just gonna log in with my other account. Okay. I wanna make sure that I can share the screen. Okay, so first, I would like to start with a summary of what we did yesterday. Okay. So usually the way I do, I label everything is pretty much the month, the day, and the year. So I'm gonna be referring to that as the class. So that was our first class. And something that I would like to just go over again from yesterday. For example, yesterday we introduced some important definitions. Here we have T as the period of a signal. And we have a relationship between period and frequency. Okay, so we have 1 over the frequency. Okay, also we were talking about the voltage RMS of a signal. That one is going to be related to the magic number 0.707 of the peak of a sine wave. Remember, this guy is for sine waves only. Okay, also we have the peak-to-peak definition. Which is 2 times the voltage peak. Okay, so quickly, I'm going to draw my coordinate system where I have time on the y, sorry, time on the x and voltage on the y. Okay, I'm going to draw my sine wave, cosine. Okay, here, for example, this guy is going to have 1 volt peak amplitude. Okay, so the RMS of this signal is going to be around 70% of that. So voltage RMS is equal to 0.707 volts RMS. Oh, I'm running out of space there. Okay, so based on this example, what will be the peak-to-peak voltage of this sine wave? If somebody can assist me there, please. Here is the defined voltage peak. What will be the peak-to-peak value for this?
2.
That will be 2. Thank you. 2 volts. Okay. Now, if the period of this signal is equal to 0.5 seconds, okay, what will be the frequency of this signal? Okay.
Two.
It will be 2 hertz, okay? Just the inverse of that period. Okay, so that was a quick, I wanted to go over this because these fundamental relationships, we're gonna come back to them over and over and over. So I wanted to have a summary of them, okay? So any questions here? Just remember, we have this guy right here. We have this one over here. And that one over there too. Period frequency, voltage RMS, voltage peak, and voltage peak to peak. Those are the ones that I want you to keep in mind. Okay, now I would like to come back and talk quickly about numerical differentiation. Here, the only thing that we're doing is calculating the slope, okay? And let's say if I have 2 data points, let's say data point number 1, and the coordinates are I'm gonna do X and Y, and I have 2 and 4, and data point number 2, and these are consecutive data points, and I have 4 and 8. Okay, if I plot those values, so I have 1, 2, 3, 4, 2, 4, 6, 8. So we have data point number 1, data point number 2, okay. The only thing that we're doing is calculating the slope between these 2 points, okay? So we're gonna have y2 minus y1, x2 minus x1, or delta y, delta x, okay? And if we apply the example here, we're gonna have 8 minus 4 divided by 4 minus 2. That's all we're doing, but we are using the spreadsheet to have a quicker way to calculate that slope between 2 data points, okay? So this is data point 2, and this is data point 1, okay? Consecutive data points. So this is the other relationship right here. Okay, any questions over here, guys? Remember, if you help me with the thumbs up, that helps me to know how we're doing. Any questions on this slide? Okay, thank you, Pedro. Thank you, Paul. Good, good. Thank you too. Good. So now this is numerical differentiation. Now, just a quick review on the trapezoidal rule. I will suggest you to practice the trapezoidal rule more than the rectangular rule, because by definition it is more accurate. Okay, so remember, we are just calculating areas. So I'm going to define I as the area. Okay, here trapezoidal rule defines area of the ith data point as the area of the previous data point, okay, plus the height of the I plus 1 data point plus the height of the current data point divided by 2. So that's the height of your trapezoid times the delta x. Okay, just be careful, because when you are managing the x values, these are subtracting, and the y values are being added. Okay, so I'm gonna have the same values that I had from before. So I have 2 and 4 on the x and on the y, and I have 4 and 8. So I have data point number 1, or I equal to 1, and data point number 2, or a subscript, it will be I plus 1. Okay, so the area, and I'm gonna use orange here, the area that we're gonna calculate is the area that I'm gonna paint with orange. This is the area. This is I. Okay. Remember, the I minus 1 area, okay, remember I is for area, capital I is the initial condition for the first calculation, okay. If the initial condition is not defined, I'm gonna assume that that's equal to 0. Okay, so for this example, I, which is equal to the initial condition, is gonna be equal to 0. Now, I is gonna be only the value of I plus y I plus 1, which is in this case 8 plus 4 divided by 2 and 4 minus 2. Okay, this is the area of the trapezoid. And that's all we're doing in numerical integration using the trapezoidal rule, okay? If in lab number 1, in the file number 3 that you use to answer the post-lab questions, initial conditions are defined. So instead of having that 0 over there, you're gonna have a value for that, okay? So just remember that. And I'm gonna upload these notes to Blackboard as soon as we are done with this class, okay? So any questions with this preview? Hopefully it makes more sense now, now that we are seeing it for the second time, okay? So are we good to start with quantifying electrical energy, which is part of lab 2? Okay, I can see 1 thumbs up. Thank you. So I'm going to switch to my other presentation. Okay, here we go. So we were talking about yesterday about different techniques that can be applied to analog signals that are being converted to digital signals. Once they are in your computer, those are digital representations of the analog signals. Okay. Now today we're going to talk about the signal characteristics. Okay, alternating current signals and direct current signals mostly. Okay. So in the mechanical engineering lab, we're going to be focusing on DC signals or direct current. Okay, so we have our DC signals. And every time that you have questions about a DC signal, you can think about a car battery. A car battery is going to provide a DC signal, okay? But what happens when you are talking about alternating signals or AC signals, alternating current signals? Here, you go from not having an alternating signal, so a DC signal will not alternate through time, okay? But AC signals will. And now that you introduce an alternating time for AC signals, you have to make the difference between low frequency signals and high frequency signals. The most common example that you have of an AC signal is a power outlet. Okay, if you take a look to the wall, you will see the wall outlet. That guy is gonna be rated. So the battery, the car battery is rated at 12 volts. The power outlet is gonna make sure that you have an output power of something in the vicinity of 110 to 120 volts, the regular one, okay? At frequency of 60 hertz. That means that the sine wave, and it is a sine wave that is coming out of the wall, is gonna be repeating itself 1/60 seconds. So it's gonna go back and forth, up and down every 60 seconds. So if you draw that signal to time, okay? And at least, because that value, 110, 120, is the RMS metric. So at least you're getting that, okay? So you might get a little bit more. And for the period, of that signal, if I already told you the frequency, remember that the period is simply going to be the inverse of that. So that's what the signal looks like, the power that is coming out of the wall. For your car battery, it's just gonna look like a straight line. It is not changing through time. Okay? So bottom line, for DC signals do not have a frequency component, okay? Or do not change through time. AC signals do, okay? Any questions here? Okay, I'm gonna continue. So here, just a quick summary of what we just discussed. DC signal is non-alternating, okay? It's just a straight line. And an alternating current, or an AC signal, as I usually refer to, and these ones, the one that we have, and we're gonna be using most of the time, is a sine wave, but you could also have a square wave, okay, or a sawtooth. This one is gonna be defined by its period or frequency, okay? And remember, the period is the inverse of the frequency, okay? And the second component is going to be the amplitude, okay? And that amplitude might change either amplitude, positive amplitude or negative amplitude, depending on the pulse, okay? But here, just have to remember that a DC signal, whatever you are reading from a DC signal, that's gonna be an RMS value, okay? RMS value is equal to the amplitude of the DC signal, okay? For example, for the car battery, if the car battery is rated at 12 volts, if you calculate the RMS value with the formula that we saw yesterday, you will get 12 volts as well, which is different for an alternating current. So here we're gonna go over a couple of examples on how you should describe your AC signals, okay? So make sure that you define the amplitude and how that amplitude is being measured. So for example, here, the amplitude of this AC signal is being described at 2.82 volts, which are measured peak to peak, and it's telling you the shape of that DC signal. Also, it's telling you the frequency, okay? Another way will be to state the amplitude, how that amplitude is being measured. For the second case, that's RMS quantity. The shape is being described, is a sine wave, and the frequency is also being defined, okay? But let's analyze the incorrect example, okay? So you have 1.4 volts, you have the shape, and you have the frequency. Why is that definition incorrect? What is it is missing if you compare it to the other two? What is the parameter that is being missed there?
If the amplitude is peak to peak or RMS.
Correct. The only thing that the last definition is missing is how you are quantifying the amplitude, okay? Is it peak to peak? Is it RMS or is it peak, okay? So pretty much the structure, the correct structure that you want to follow is the amplitude definition, shape, and frequency. Okay, so amplitude definitions, you have peak, peak to peak, and which other amplitude definition do you have?
RMS.
RMS. So I'm just gonna do it right here. RMS. I just do that dotted line just as a constant, okay? Because remember, the RMS value is only a discrete value that quantifies the signal in a certain period of time. Okay, so we have three different amplitude definitions. So I'm just gonna draw some arrows. Right there. So I'm gonna continue. Here is very, very important that you know and that you are aware that DC signals and AC signals can be combined together, okay? For example, here on the figure on the right, you have your time axis. I'm actually gonna do a different color. Your time axis. And you have your amplitude, your voltage on the Y. Okay. Here, as you can see, if you take a look to the signal, you can see the peak of this signal right here, a negative peak over here, or another negative peak here, positive peak here, and another positive peak at the very beginning of that signal. Okay. If you dissect this plot, you will find that the alternating component of this signal moves back and forth along the DC line or the DC offset right here. So from this point all the way to the 0 axis, that will be your DC offset. Why DC? Because that offset belongs to the DC component of your signal. Okay, so I'm going to keep this. I'm going to create a new slide right there. And we're gonna do a quick demonstration. Okay, I have a signal, an AC signal, voltage, and this signal is 2 volts peak sine wave at 1 hertz. Okay, that's my AC signal. So you know that the peak that this signal is going to reach is going to be +2, -2. Sine wave at 1 hertz, up and down, up and down. So I plotted that signal for 2 cycles. Okay, if I plotted that signal for 2 cycles, what is the total time length of that signal? In order to answer that question, you have to remember that period is equal to 1 over the frequency. How many periods or how many repetitions of that sine wave can you see in that plot? 2. And if you know that you are seeing 2 cycles of it, and you know the period of that sine wave, what is the time length? What is the time at that point? It is 2 seconds. Okay, thank you. Okay, so now I'm gonna add a pure DC signal to that AC signal. This DC signal is going to have an amplitude or RMS value of 5 volts. Okay, it's just a straight line. It doesn't vary through time. What is the result of adding these 2 guys together? Let's analyze where the signal, let's analyze the signal at time equal to 0. You are adding these 2 together. What is the amplitude of the sine wave or the AC signal at time equal to 0? Time equal to 0 is right there. Okay. And what is a mark? And what is the amplitude of the DC signal? The DC signal at time equal to 0 is 5, right? So the first data point for this addition of signals should start at 5 volts. because those 5 volts are defined by the DC offset that is coming only from the DC signal. Okay, now if we were to analyze the amplitude, the peak amplitude of your signal, at that point is going to reach the 7th volt mark, and it's going to cross again the DC offset. It's going to go down. At this point, what is the amplitude? At 3/4 of a cycle of that sine wave. Is it 3/4? 1, 2. It is 3, correct. And finally, it goes back to 5. At which time you have a full cycle of that sine wave? At 1 second. Okay, so here, right here, you see a signal that is composed by an AC and a DC component, okay? So that's a final signal. Any questions here? Okay. Let's continue. Let me go back to that one, to the previous slide. Your instruments in the laboratory, the oscilloscope in particular, is going to have 2 different options. One option is going to be one called AC coupling, okay? Which means that only AC signals are allowed, okay? And for DC coupling, all the components, AC and DC components, are allowed. Okay, this means that if you are interested in seeing both components of a mixed signal, you will have to have your DC option on the oscilloscope. But if you are only interested in the AC component of that mixed signal, then you will have to apply AC coupling on. Okay, so think about how in this example, if you focus on the figure on the right, okay, let's say you have, that's your initial signal, the figure on the right. If you apply an AC coupling, what do you end up having? What is being left behind, and what is being kept after that AC coupling application? Is the figure on the top left or the figure on the bottom left? What would be your guess?
Top left, you said AC, right?
Top left. Remember, AC signal, AC coupling will only allow the AC component of the signal. And this is the AC, a pure AC signal. And this is a pure DC signal. Okay. Now let's repeat and let's start over. The figure on the right, that's your initial signal. What will happen if you apply a DC coupling to that signal. What do you see? You have three options. You either see only the AC component, or only the DC component, or both. If you have DC coupling on, and you either have one or the other on, you cannot have both at the same time, you will see the same initial signal. You will see the DC offset or component, as well as the AC signal. Okay. We're gonna do, we're gonna use that option on the oscilloscope in the lab. So all the instruments that we're gonna be using in the lab, all of them are gonna have a usable frequency range. Okay. Remember that the frequency range is the usable frequency range is gonna be the limit frequency wise of an instrument, which is going to keep the measuring signal without any distortion, okay, without affecting the magnitude, okay. The usable frequency range, also defined as FC, okay, is also called the cutoff frequency. Okay, here, this plot right here, it is not in the time domain anymore. It is in the frequency domain. And in the frequency domain, we're gonna be using hertz. Okay. So this is just a new definition that you will we will have to keep in mind. And the cutoff frequency, or the usable frequency range, is defined by the 3 dB down point. Okay. Because this plot is in gain dB. And how do you calculate that gain dB? That gain dB is being calculated by 20 times the log 10 base of G, and G stands for gain. Okay. And gain is defined by voltage output divided by voltage input. Okay. Later we're gonna come back to that expression, but here is just the definition of gain dB, and also the definition that we need to keep in mind, or concept, is the cutoff frequency. If you hear about cutoff frequency, you gotta have the idea and know that you are talking about the usable frequency range of an instrument, okay? And this is gonna be defined in hertz. We're gonna come back to this later on, okay? I'm gonna keep those. Okay. Now we're gonna start talking about filtering. Okay. Let me share that. Okay, so we continue with aspects of filtering. When you, let's say, if you, I don't know if you guys, for example, I have a Brita filter, like one of those pictures with a filter, right? When you are filtering the water, what are you keeping? What is being filtered? What is being kept out, the output of that picture, and what is the input into that filtering system, and what is the output of that filtering system. Let's work that analogy before we introduce the concepts of the lab. What is the input into that Brita filter? Is the water with what?
The water with impurities.
Mm-hmm. Okay, and you are putting that solution, okay? This is your input into the picture, right? You have your filter, okay? What is the output of that filter?
Just the water.
Just the water. Okay. So in the mechanical engineering lab, we're gonna use filters in a very similar way, where we have different signals, and sometimes we want to keep out certain contaminants or particular signals out of our final result or our final output. Okay, it's very, very straightforward, but we have different ways to do it. Okay. The first thing that I want you to keep in mind is that when you see a plot like this, you are not in the time domain anymore. You are in the frequency domain, okay, where we are using hertz. So here, I'm showing you 4 different filters: a low pass filter, a high pass filter, a band pass filter, and a band stop filter. Okay. All of these, the plots that you see right now, no, let me use another color. I'm gonna do them in green. The green curves that you see in this quad plot all of these are called response functions. In this case, these are filter response functions, okay? The way each filter is gonna work is defined by the shape, obviously by the shape of these plots. The low pass filter is going to keep frequencies below the cutoff frequency relatively unaffected. That means that when you think about that, is the filter is gonna keep low frequency signals and is gonna filter out signals that are above that cutoff frequency. Remember, FC is equal to the cutoff frequency. Okay, and we're gonna talk about particular examples on those signals. Okay, but what I want you to keep in mind is that always think about the flat portion of your filters, because that flat portion is going to tell you the signals that remain relatively unaffected. What you can see on the y-axis is a voltage output, voltage input ratio. Okay. And this is defined as the gain, or G. Okay, so what you have right here is G, regular G. In the previous slide, we were having gain dB or GdB. Okay, but here is just regular gain. If you are in the flat portion or the plateau of these filters, that means flat portion means a gain of 1. Let me just improve that writing. Portion. This is very, very important that I'm gonna keep asking you about. Okay, if you know that the gain in that portion of the filter is equal to 1, I want you to come back to the main expression. Gain is the ratio between the output and the input. Okay, let me introduce new slide. Okay. And we're going to discuss a low pass filter. We have frequency on the x-axis in hertz, and we have gain, regular gain in the y. Okay, remember that gain is defined as output divided by the input. Okay, so my response function of this filter has a flat portion at the beginning, and then it starts to roll off like this. Okay, the knee or the cutoff frequency of that filter, I'm going to define it at 100 hertz. Okay, that's my filter. If you know that at this point, at the flat portion of the filter, gain is 1, and I have two signals. I have one input signal. I'm gonna call it S1. Signal 1 is defined as a 5-volt peak sine wave at 10 hertz. Okay. And if you remember the diagram that we did for the water filter, we have a filter, a low pass filter with a cutoff frequency of 100 hertz. That filter is going to have an input, and that filter is going to have an output. Okay. My signal 1 is the input into that. VI is equal to 5-volt peak. And that signal is at 10 hertz. So probably 10 hertz should be around there. Okay, remember, it is you are just locating the frequency of the signal. That has nothing to do with the filter. The filter is its own entity. But now you come with the signal and you apply that input through that filter. Now you want to measure the output of that. Okay, you know that at the flat portion of that filter, what is the gain equals to? Guys, what is the gain equals to when you are at the flat portion of that
1
filter? It is 1. And if you know the gain and if you know the input, you can calculate the output. Let's do it. Gain is equal to 1, voltage output 5 voltage peak. Voltage output is equal to 5 volts peak. VO is equal to 5 volts peak. And in experiment number 2, tomorrow, we're gonna do this in the lab, and on Thursday, everybody else remotely. Okay, so this is one example when the only signal, you only have one signal, and that signal, the frequency is way below the cutoff frequency. Okay, now another example. I'm going to bring a second signal, S2 is going to be, and this is going to be a different signal, okay? It's going to have the same amplitude, 5 volts peak. It's going to be a sine wave at 100 hertz. Up there, I'm going to quickly draw our low pass filter. Remember, the filter is defined in the frequency domain, and on the y-axis we have gain. This filter has a flat portion and then rolls off. The roll off is defined by the cutoff frequency, FC. And the FC, we're gonna have the same filter as before that is defined at 100 hertz. As you can see, the frequency of signal number 2 matches the frequency of your filter. Okay? Now, let's analyze the input output of this filter. So we have a low pass filter with a cutoff frequency of 100 hertz. The input is 5 volts peak. Okay, what will be the output? Were we able to calculate the output voltage VO in the previous example, right? But what was the parameter that we knew in order to calculate the output?
The gain.
We knew the gain. Okay. Now, if I tell you that at the cutoff frequency, the gain at the cutoff frequency is equal to the magic number. What is that magic number, if you remember?
0.707.
Correct, 0.707. Knowing the gain at the cutoff frequency, we're going to be able to calculate that. Remember, gain is equal to voltage output divided by voltage input. We know 0.707 is equal to voltage output, 5 volts peak. Voltage output is going to be 70.7% of 5 volts, 3.53 volts peak. Okay, remember, the filter was the same. And let me use green for that. The filter was the same for both cases. The only thing that changed was the input signal. In the first case, the input signal had a frequency of 10 hertz. That means that the frequency was way, way below the cutoff frequency of the filter. Okay. In the second case, the input signal had a frequency of 100 hertz that matched the frequency, the cutoff frequency of our filter. And by definition, the gain at the cutoff frequency is equal to the magic number, 0.707. Okay. Just to, and this is gonna be worth it, I'm gonna do a third case. And can somebody tell me what will be the third case? So the first case was below the cutoff frequency. The second case was at the cutoff frequency. So the third case is going to be beyond the cutoff frequency. And it's the same filter again. 100 hertz. FC, 100 hertz. So we have a third signal, which is going to have 5 volts peak. It's going to be a sine wave, but this time it's going to be at 1 kilohertz. Okay. Which means that it's going to be our signal, and I'm going to use blue. So this is S3. Remember, a sine wave, you know, a sine wave in the time domain, it looks like the function that you know and you are accustomed to. In the frequency domain, a sine wave is just one discrete line. So that this blue dotted line is the representation of or where that sine wave or signal 3 falls or is related with respect to your filter. Okay, and remember, S3 has a frequency of, and I'm gonna label it F3, 1000 hertz. We start. So we have our filter defined, and remember this is a low pass filter. And the cutoff frequency is equal to 100 hertz. And remember, the filter is independent from your signal. Okay. Now, the input into that filter is VI at 5 volts peak. In order to calculate the output, we either know the gain defined by the cutoff, by the response function, okay, remember that the response function is this line, the green line. Response function or you know, or you measure the actual output of that filter. In this case, I'm going to give you the output of this filter. The output, the measured output coming from the filter is 0.05. Knowing that, what will be the gain of the filter at 1000 hertz? 5 0.05 voltage peak and 5 volts peak. Okay, so we have, oops, 0.01. That would be your gain. Okay, so just keep in mind that gain is voltage output divided by voltage input. You need to know 2 out of those 3 parameters to solve the problem. Okay, so now let's take a look to a quick summary of the different gain values. So in case 1, the gain was equal to 1. Case 2, the gain of the filter, and remember, the gain is defined by the filter, 0.707. Case 3, gain was 0.01. Let's make a quick summary of those results. Okay, summary. So we have case 1. The gain, and remember, is related to the filter. The gain at the flat portion was equal to 1. And I'm gonna flat portion. Case 2, what was the situation that was discussed? I'm gonna go back. At which point, frequency-wise, we were analyzing this case? We are analyzing the filter, but what was the point? Look at your x-axis for this case, and what was the point that we were analyzing frequency-wise at the cutoff frequency, okay? So case 2 was at cutoff frequency. And case 3 was way beyond cutoff frequency. FC cutoff frequency. Okay, so what was the gain of the filter in case number 2?
0.707.
The magic number, 0.707. Correct, thank you, Paul. And what was the gain for case number 3? Gonna go back. That was 0.01. Am I missing units as I'm defining gain? I am not, because gain doesn't have is dimensionless, okay? Because you have, in all these cases, we had volts peak at the top, volts peak at the bottom, okay? Regardless of the amplitude definition that you're using, you could use voltage peak, you could use voltage peak to peak, or voltage RMS. They have to be the same at the top and at the bottom, okay? Otherwise, the gain will be incorrectly computed. Any values for the gain, and I'm gonna go do a quick summary here of the response function for the low pass filter. So we defined 3 sections, okay? And I think I'm gonna do it this way better. I'm gonna have my filter at the bottom. I have my flat portion. Then I have the vicinity with the cutoff frequency, and then the final roll off. So I have case 1. I have the vicinity of case 2. So remember, flat portion or plateau, gain is equal to 1. Oh, that's, let me improve that G. Remember that this was just a discrete frequency line that we analyze again. Okay. Gain at cutoff frequency is equal to 0.707. And the third case analyzed the filtered being at 1,000 hertz. Remember that the cutoff was set at 100 hertz. The last signal that was analyzed was rated at 100 hertz, and the first signal that we analyzed was at 10 hertz. Okay, so here the gain was equal to 0.01. So if you see the transition, I'm gonna describe with my black pen the response function of this filter. It starts flat. Oops, starts flat. 1, G is equal to 1, equal to 1, equal to 1. There is one point where that flat portion starts to roll off, and it starts decreasing from 1 to 0.9, 0.8. At this point, it reaches 0.707. That means that whatever you're getting out of that filter is being attenuated, is being filtered. If you keep moving forward frequency-wise, your gain is gonna start decreasing. 0.5, 0.4, 0.3 is gonna start at the higher you are in frequency, the faster it's gonna start dropping till you reach 0.01. If you go to 10,000 hertz, then it's gonna be around 0.001 gain. Okay, and those values are gonna help you to know what is the output voltage that you get after playing your input signal through the filter. Okay, so I want to keep it general in the sense that just have in mind 3 different zones or areas. The first one, it will be the flat portion. The second one, it will be the region defined by the vicinities of the cutoff frequency. And then the third region is the one that is way past the cutoff frequency. Okay. At this point, we don't need to get any more into depth with this. Okay. But as long as you remember that at the flat portion of the filter, gain is equal to 1, and the gain at the cutoff frequency is equal to 0.707. We should be okay. Okay. Any questions? Okay. So I would like to go back to slide number 2 here. As you can see, different filters are gonna have the flat portion of the flat portion of the flat region situated in at different frequencies. If you take a look to the high pass filter top right, you see that it is pretty much the mirrored version of the low pass filter. Okay, you have very low gain values before the cutoff frequency, but then, so I'm gonna do green. As you move higher in frequency to the right, okay, then you reach the point where the gain is equal to 0.707. You can move it forward, and then you reach the flat portion again, which means a gain equal to 1. In this case, the high pass filter is going to keep frequency content beyond the cutoff frequency. What the low pass filter did, the low pass kept frequency content below the cutoff frequency. Okay, the band pass filter is gonna keep frequency content relatively unaffected within the flat portion of that frequency response. So this is the keep area. Okay, everything outside the keep area is gonna be filtered out. Okay, the band stop filter, keep the flat portion, keep flat portion. Okay, keep okay, so all those keep regions were defined based on a gain of 1. Remember, flat portion means gain of 1. And keep in mind that this is defined by the filter, has nothing to do with the signal that you're gonna work with. Those are 2 different processes. Okay, and just to, let me just keep this. Let's talk about different different scenarios when filtering is applied. Okay, one I like to talk about a lot is music, either through a streaming medium or through your car or at home. Okay, and a lot of these concepts are gonna be you're gonna see them in the lab in quantifying electrical energy. So the first one that I would like to talk about is the equalizer, an equalizer. Okay. An equalizer is nothing but a bunch of band pass filters. Band pass filters. Defined in series. You have a band pass filter having a cutoff frequency set at 31, then another bandpass filter with a cutoff frequency set at 62, and then you just have the same 125, 250, 500, 1,000, and so on. Okay. When 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. When you are in this region, in the region below 125 hertz, these filters allow you to control the bass of your music or the low frequency components of the music you are equalizing. Okay. Then you have on the other side you have the treble, which is the high frequency components of your music. Okay. So let's say if we were listening to, let's say, what would be a good example? What is one of the most popular songs right now? Not reggaeton. Let's do. Let's do pop music. For example, and focus on a drum set. Okay. Not on a drum set. You know that a drum set has the toms or the big drums, and also it has the snares. Okay. When you hit one of those, you are creating high frequency noise, or you are exciting the high frequency components, which are beyond 2000K and beyond. When you are hitting one of the floor drums, you are generating a low frequency component. Okay. So let me show you. For example, I'm gonna try to, I don't know how good the sound is on your end, but I'm going to go from low frequency noise to high frequency noise, trying to emulate that with my throat, with my voice. Okay, so I'm gonna start at low frequency. So it's gonna sound something like this. So I'm gonna try to keep that tone, which is a low frequency tone. Okay, and then I'm gonna increase the frequency of that tone. Okay, 1, 2, 3. And then just think about how for a low frequency signal, the a low frequency signal is gonna be a sine wave that is very, the cycle of that sine wave is gonna be very, very small. Okay, so as you increase the signal, the cycle of the frequency is getting higher, smaller and smaller. Okay, but if you take the inverse of that, then you have the high frequency. Okay, so every time that you think about low frequency signals and low frequency and high frequency signals, you can make the distinctions between bass and treble. Okay, and here what you control with these knobs is the gain. Okay, the gain of those bandpass filters. Okay, if you are interested in focusing more on the bass, you will increase the gain of that filter, of those filters. Okay, if you are interested in increasing the high frequency, let's say you are focused more on the voice, you want to increase the gain in higher frequency, in the higher frequency components. Okay, but again, these are just bandpass filters that you either increase the gain on those filters or decrease the gain. And remember, these are bandpass filters. Can somebody give me another example of maybe or low frequency noise? Where do we hear like that bass like noise? Or maybe a high frequency noise? Okay, so wells, that's high frequency noise. High frequency noise doesn't mean that it has to be high amplitude. Okay, is related to the frequency content of that signal. Okay, so if we focus on sound coming from animals, would you say that the bird chirping is that low frequency or high frequency noise? High frequency noise. Now let's talk about the barking of a dog. Would that be in the lower frequency side of things or in the higher frequency side of things? Absolutely, it depends on the size, but it's gonna be definitely something below the mid range. Okay, and definitely way lower than the birds. Okay, so now we have a good reference, a good everyday reference of what low frequency and high frequency components are. So, and here, just remember, these are a bunch of bandpass filters that you can control the gain. So remember, this one is gain dB. Now, this is a good time for us to remember what gain dB is defined as 20 times the log 10 of the gain. Okay, and you remember that the gain is equal to voltage output divided by voltage input. And you will find that definition at the end of the previous presentation. All these presentations will be uploaded to Blackboard once we're done with them. Okay. Now, let's go back to the usable frequency range of our instruments. Okay. Earlier, what was the other name that we use for usable frequency range? Do you remember?
Cutoff frequency?
Cutoff frequency, exactly. So the usable frequency range is also defined by the cutoff frequency, okay? Each instrument is gonna have its own, oops, okay? Here, judging by the scale, the flat portion of the oscilloscope frequency response is gonna be longer frequency-wise than the multimeters, which means that you're gonna be able to measure signals that are higher in frequency than the multimeter. Okay, in the lab, we're gonna have an oscilloscope that is gonna be our reference, or is gonna be our voltage input, and also we're gonna have connected a multimeter that is gonna be our voltage output. Okay, we're gonna use these two to calculate the response function of the multimeter and to define where the cutoff frequency of the multimeter is, because by definition, we know that the cutoff frequency of the oscilloscope is something around 2 megahertz. Okay, the one in the multimeter is way lower, but we're going to analyze that during the experiment. Okay, when you turn on the AC coupling on these instruments, remember before there was a flat portion all the way, but now the flat portion is limited. Okay, so here the frequency responses of these two instruments, and remember this is in the frequency domain, hertz, hertz. When you turn on the AC coupling, then your frequency response behaves like this. You have the gain is low and then keeps increasing till it reaches 1. Gain remains 1 during the flat portion and then starts to decrease. Okay, and the same for the multimeter, but the flat portion is shorter, okay, because the usable frequency range is shorter too. So you have gain, which is low, start increasing, remains 1, starts dropping. Okay. When you have the AC coupling on, you got to remember that only AC signals are allowed. Okay. Because remember, the DC signals, they do not have a frequency component. They do not vary through time. Okay. And if they don't vary through time, you can imagine them as a DC signal. You can think about it as an AC signal at 0 hertz. And where is the 0 hertz line located? Right at the beginning of those plots. Frequency here is equal to 0 hertz. Okay, so when you turn on the AC coupling, you are leaving out DC signals. Okay, the previous example did not have AC coupling on. This was DC coupling, which is going to keep both AC and DC components. Okay, that's how the frequency response function is changed when you have AC coupling on. This AC coupling is achieved, could be by a combination of a high-pass filter as well. Remember that the high-pass filter, the purpose is to keep high frequency signals, okay? But if you use that in combination with an oscilloscope, okay, you're gonna be able to leave out DC components of that signal. Just let me go back to the main plot right here. On the top right, you have the high-pass filter, which the high-pass filter, the purpose is to keep high-frequency signals. The purpose of the low-pass filter is to keep low-frequency signals. Okay. Now, this is just another quick example. Our human hearing range, is shorter. So I'm going to call it range 1 is shorter than a dog's. Okay, because here comes the thing that everybody's gonna be able to relate to. Remember, on the x-axis you have frequency. Every time that you see these response functions, you have frequency on the x-axis. Now I'm gonna bring up the dog whistle. The frequency of the dog whistle is outside our hearing range, but it is inside the dog's range. That's why when somebody blows the dog whistle, we don't hear it, but the dog is able to catch it because it is within its range. So it's going to be very similar to the filters. If the signal that you're trying to measure is outside the range of your filter or outside the range of your instrument, you will not be able to visualize that signal. You will not be able to measure it. Okay? You have to be able to identify the properties of the filter, the characteristics of the filter that you're using, the characteristics of the instrument that you're using, what is the usable frequency range of the instruments. Okay, because if you're trying to measure something that goes beyond the usable frequency range of your instrument, then you're gonna be in a bad situation. Okay, so that's another good example of usable frequency range. Sensors are gonna be the same way too. When we get to start working with accelerometers, okay? So we have here 2 accelerometers that work on the different bases. One is driven by a piezoelectric material inside that sensor, which allows that sensor to have a wider range, a wider usable frequency range, or a higher cutoff frequency. And a strain gauge based accelerometer is going to have a lower cutoff frequency. Okay, FC1 is going to be greater than FC2. Remember that FC is cutoff frequency, but also defines the usable frequency range. Everything has a usable frequency range. Sensors, instruments. In the instruments, you have oscilloscopes, you have multimeters, you have filters. Okay, we have to be aware of those, because sometimes you will not be able to know what the exact frequency of the signal that you would like to measure. You will not know that one, but at least you have to make sure that because all these cutoff frequencies or usable frequency ranges are going to be provided by the manufacturer. Okay, and the signals that you will be measuring in engineering applications are defined by n variables. Okay, so the more you know your instruments, the better the chances are that you're going to have a useful measurement. Okay, and here is just the block diagram of the equalizer. Okay, and you can see the bunch of this equalizer, for example, has a low pass filter at the beginning, has a band pass filter, so low pass, band pass, band pass, band pass, and at the end, a high pass filter. Okay, so when you turn up and down each option on your equalizer, you either increase the gain. Increasing the gain means that increasing the gain goes from 1 and higher than 1. That's when you are increasing the gain or making the sound louder, if you will. And when you decrease the gain is because you want to attenuate that frequency content. Okay, And here is maybe an example that everybody can relate to. If you know that what you're seeing on the right is a classical guitar. A classical guitar, the strings are made out of nylon, okay? A more modern guitar, I usually refer to this one as a classical guitar, or I also, some of them are defined as a Spanish guitar, and an American guitar will be the one that has the steel strings, okay? So right now we are looking at a nylon string guitar. If we start from right, which is gonna be usually the thinnest string, that thinnest string is gonna be the one that has the highest frequency. If you pluck it and you take a measurement, a microphone measurement on that, you're gonna be able to see that the period of that string is gonna be 1/329 hertz. As you move to the left, or you start playing or getting the free response of each string, for the second string, then it's gonna start increasing that that frequency. It's gonna go from 329 to the second string of 246, and then you keep going all the way to the sixth string that has the lowest frequency at 82 hertz. Okay, and I might have. So I have my guitar here. Let me see if it is not tuned, but I'm gonna be able to. And I'm missing one string, but you're gonna be able to hear it. Just give me 1 second. Okay, so right now I'm missing the sixth string, but I'm just gonna play the free response of the first string. Okay, here it goes. Again. That decaying response is the period of that decaying response is around 1/329. Remember, frequency period is equal to 1/the frequency. Now I'm gonna plug the second string. Now it is becoming more of a bass, a low frequency sound. I'm gonna do the third one. Dun, dun. The fourth one. How is the sound? Is it super crappy, or is it good enough? Can you distinguish between the strings?
You can distinguish.
Okay, thank you. And then the fifth one. Okay. Now, right now is just the free response of the first string. What if I shortened the length of the string? I'm gonna shorten it by maybe an inch, then 2 inches, then 3 inches. What was the frequency progression there? Was I going from low frequency to high frequency, or from high frequency to low frequency? Let me do it again. Low low to high frequency, okay? So if you were able to take, and I'm gonna show you later in the course, I'm gonna show you some microphone measurements on a very similar experiment, and we're gonna convert that time response into a frequency signal. So you can see how the progression of those strings go from the left-hand side of that frequency axis, and it moves higher in frequency, okay? So next time I am not doing that with my voice anymore. I forgot the guitar till I saw the slide. Anyway, so with that, we conclude the quantifying electrical energy topics. Now we're gonna do a quick overview of the instruments that we're gonna use tomorrow and the day after. Let me save this. Now let me bring the final presentation. I'll share it. We're almost there, guys, so just bear with me. Oh, sorry. I was just asking you to bear with me. We're almost done with the final presentation. Yeah. So it was pretty much my audio being choppy, right? Being chopped. Cool. Okay. Let's start. Okay. So before I show you more details on the instruments that we're gonna do, so far, what were the instruments or devices that were discussed in the previous presentations?
An oscilloscope and a multimeter.
And what was another device that we talked about the response function a lot? Filters, exactly. So far we discussed oscilloscope, multimeter, and filters. And filters can be set in different ways. You can have a filter set low pass, a filter set high pass, band pass, or band stop, but it's still a filter. Here we have the Tektronix TBS 1032. It's a digital oscilloscope, and you're gonna be able to measure AC and DC signals. Okay, this is what it looks like. The first controllers that you're gonna see is gonna be the vertical controls. So from top to bottom, the first row in this, let me grab my laser pointer. The first row right here is the position control. Okay, then you have the menu buttons, and you have 1 and 2 for channel 1 and channel 2. Okay, then you have the scale, the vertical scale for each channel. Okay, the vertical scale is going to define if are you able to see the division, the vertical division lines? Sorry, the horizontal division lines right here.
Yeah, we can see them.
Yeah, so those are gonna be, the scale is gonna be defined by these two controllers, okay? You have yellow color for channel number 1 and blue color for channel number 2. That's what you're gonna see on the screen. Blue for channel 2 and yellow for channel 1, okay? So here is just a zoom in into a close-up on those options. So you have 2 channels, okay, for your 2 analog signals. Those analog signals can be AC or DC, okay? The position is gonna change the vertical origin or center of the signal voltage-wise, okay? You have the menu button with 1 and 2 that is gonna show the main menu of the oscilloscope, all the different options that you're gonna have. The scale is gonna change the oscilloscope vertical scale, okay? And at the bottom, you have the famous BNC connectors, okay? Which that's gonna be the cable coming from the function generator, where we're gonna get those AC signals or power supplies, or power supply, where we're gonna be getting the DC signals from, okay? So right there at the bottom. So when you modify the scale, just take a look to the top yellow rectangle. When you modify the scale, you're gonna see the change on the bottom left of the screen on the oscilloscope, okay? As you move it clockwise, the scale is gonna increase. It might go from 200 millivolts to 500 millivolts, then to 1 volt, 2 volts, 5 volts. That means that each division for this particular case is equal to 200 millivolts, okay? So if you know that each division is around 200 millivolts, more or less, what is the amplitude of that signal that you see there? At this point, what is the voltage of that signal? Just eyeball it.
A little bit more than 400 millivolts.
And less than?
Less than 500.
And less than 500, okay? That's kind of half of the in-between divisions. So the vertical scale is gonna give you control over that portion. Right now, are we using channel 2 based on the picture that you see?
No, we're using channel 1.
We're only using channel 1. If you have had connected channel 2, you will see a blue voltage quantity right here, and you will see something else in blue, okay? But in this case, we didn't have a second signal, okay? And that's all for the vertical controllers, okay? So for the position, for channel number 1, the vertical position is going to be defined by that marker over there. If you would like to bring that marker to the 0 line of your screen, you will have to rotate it either one way or the other to get it centered, okay? But the little mark over here, that's the origin of your signal, okay? Sometimes you play with the position knobs to get, maybe to try to align the peak of any signal to a certain division of your screen, but that's how it goes, okay? Remember, these are only the vertical controllers. Now let's talk about the horizontal controllers. You're gonna have position. Let me get a better color. Position and a scale. they're gonna do the same thing as the previous position and scale knobs, but this time they're gonna control the time axis. Oh, now I need a lighter one. Or the horizontal axis. Okay, if the scale knob is defining 50 nanoseconds, that's going to tell you that the divisions of that oscilloscopes are worth 50 nanoseconds. If you would like to have a coarser scale, then you will increase that scale, and it's going to go from 50 to 100, then to point, and you're going to increase and decrease, and it can go all the way to 1 second. Okay, but at that point, that's what it is based on this result. And for the position knob, this is the indicator of the center, horizontal wise of the signal. Okay, usually myself, I like to have both the vertical center and the horizontal center of them aligned with my axis of the screen. But sometimes it helps to move it back and forth. So you can, maybe you are trying to get that peak in the very center, but originally that signal is not there. You just want to move it a little bit with a horizontal position knob, just to get a better reading on that peak. Okay, so it's very, very straightforward. But the best option that you're gonna have and you're gonna be able to use is the auto set function. If you have already connected your signal, either 1 or 2, on the BCN or the BNC connections there, you're gonna be able to press the auto set button, and the oscilloscope is gonna automatically adjust the vertical and horizontal scales for it. Okay, so if you're running out of time, you can just auto set, and you will get the best picture of those analog signals that you are interested in. Okay, always remember, auto set is gonna be your best friend there. Now, here, the thing that I want you to remember, anything coming from the multimeter is gonna be an RMS quantity. Okay. For the first row on the left rectangle, you're gonna be able to measure DC and AC voltage. So line ... means DC, little sine wave means AC. Okay, V for voltage or volts. The second column is you're gonna be able to measure DC and AC current. Okay, and on the ohm or the omega, that's gonna be to measure resistance and also to measure the frequency of the signal. Okay. Also, we're gonna be using power supply. This power supply is gonna be able to generate DC voltage and DC current. Okay, this little guy doesn't generate any alternating signals. Okay, only direct current signals. The function generator, though, this is the guy that is going to help us to generate those alternating current signals. Okay. So on the left, you're going to have the frequency multiplier knob. Okay. On the middle, on the top middle, you're going to have the range of the frequency. Okay. For example, if you wanted to set the frequency of a sine wave, okay, so you have, let me get my color. you press the sine wave button for the shape of the wave, and you want it to be at 200 hertz, then you're gonna press 200 range, and you're gonna multiply it by 1. So that way you're gonna set the frequency, but also you need to set the output or the amplitude of that signal, okay? So that will be your amplitude regulator. Do you want it to be at 1 volt peak? If you do, then you will have to check that amplitude with the oscilloscope. If you would like it to be 1 volt RMS, you will have to check that amplitude directly to the multimeter, because remember, the multimeter gives you the RMS values, okay? And you're gonna, the output of your function generator is gonna be the input into your oscilloscope, okay? And it is the guy at the bottom right there. Also, you're gonna be working with a filter, an analog filter, okay? And remember that input-output relationship that we were talking about. You have up to 2 channels, which means you can have up to 2 different signals being filtered, okay? So on the left, you have your input, and on the right, you have the filter signal or the output, okay? You use the numerical keyword to define the cutoff frequency of the filter, okay? And those are the instruments that we're gonna be using tomorrow and the day after, okay? If possible, maybe tomorrow after the presentation, I'm gonna send you more information on these instruments, okay? But for now, this should be enough. So any questions before we log off? We are pretty much at the end. And as soon as we log off, I'm gonna upload all these slides to Blackboard for you. So if you don't have any more questions, feel free to log off. Okay. Awesome. Good, Mark. You too. Take it easy, Mario.